Good afternoon. My name is Gadi Dechter. I'm the Vice President for Communications and Government Affairs here at Princeton University. It's my great pleasure to welcome you all to this news conference and celebration today, in which we celebrate John Hopfield, one of the two winners of the 2024 Nobel Prize in Physics. Professor Hopfield is the Howard A. Pryor Professor in the Life Sciences Emeritus and Professor of Molecular Biology Emeritus at Princeton University. He holds associated faculty status in physics and neuroscience. Thanks to everyone for joining us today, and thank you to the team that made today possible. We will start with remarks by the president of Princeton University, Chris Eisgruber, followed by brief reflections from Murthy, director of the Princeton Neuroscience Institute, and Jim Olsen, chair of the Princeton Physics Department. After that, Professor Hopfield will speak, and when he concludes, I will put to Professor Hopfield a handful of questions submitted earlier by members of the press. This press conference will be recorded and made available on Princeton's website. And now I'm pleased to hand it over to the 20th president of Princeton University and a former Princeton undergraduate physics major, Christopher Eisgruber.
Thank you. Thank you, and welcome to all of you. We do still have a few more seats that are down in the front. For those of you who join us online, we are before what is literally a standing room only audience here in one of our largest auditoria at Princeton University to celebrate this extraordinary day. So it's my pleasure to welcome you to this press conference celebrating the Nobel Prize in Physics winner, Professor John Hopfield. And I think we did a round of applause earlier, and I know it's remote, but if everyone could join me in a round of applause for John Hopfield. Wow. Nobel Prizes are so special for so many reasons, where the world stops for a moment and recognizes the special importance of fundamental research and scholarship. And I think here at Princeton University, we have a tradition of celebrating these prizes the way that some universities celebrate national athletic championships and things like that. It's a moment really to take pleasure in what we do. And John, we are so grateful to you for making this possible for us. We are thrilled that Professor Hopfield is able to join us remotely from the United Kingdom. And John, I really hope that you can feel Princeton's campus buzzing with excitement and pride in your honor all the way across the Atlantic. True pioneers are what the Royal Swedish Academy of Sciences called John Hopfield and co-winner Geoffrey E. Hinton of the University of Toronto in awarding today's Nobel Prize in Physics. The laureates were recognized for foundational discoveries and inventions that enable machine learning with artificial neural networks. Machine learning has transformed our world, used today in everything from smartphones to self-driving cars. At Princeton, Professor Hopfield is the Howard A. Pryor Professor in the Life Sciences Emeritus and Professor of Molecular Biology Emeritus. A polymath, his groundbreaking career spans physics, neuroscience, biophysics, molecular biology, and chemistry. His Nobel Prize-winning work shows how extraordinary discoveries are possible when brilliant thinkers are given the freedom to explore across traditional disciplinary boundaries. Professor Hopfield beautifully exemplifies Princeton's commitment to curiosity-driven research, and his work demonstrates the power of profound ideas to address some of the world's most pressing challenges. Speaking to Princeton's Office of Communications earlier this morning, Professor Hopfield said that he hopes his Nobel Prize shows how society benefits when scientists are able to pursue this kind of curiosity-driven research. And I'm going to quote from John's remarks earlier today: "The science which advances technology is the science that gets done for curiosity's sake much earlier. Science that doesn't sound as though it's very useful becomes ultimately the generator of technologies which are so interesting, useful, and which one relies on to keep making things work better." John, I very much hope that Congress is listening as you speak. The fundamental science that gets done today is essential to the applications of tomorrow. Our future depends upon generous funding for the National Science Foundation and other agencies that make curiosity-driven research possible. Professor Hopfield is also a pioneer of neuroscience at Princeton. Faculty colleagues call him a towering figure in the field and a founding father in the creation of the Princeton Neuroscience Institute. He is also considered an inspiration, mentor, and guiding light to the next generation of award-winning Princeton neuroscience faculty. We are grateful to have some of Professor Hopfield's colleagues with us now to speak more about his impact on Princeton science and the world. And I think at this point I'm going to turn things directly to the director of our Princeton Neuroscience Institute, Professor Mala Murthy. Mala.
Thank you, Chris. It's so wonderful to be here today, and we're just so immensely proud to celebrate the profound impact of our colleague and collaborator, John Hopfield, as it was recognized today in Stockholm and around the world. John worked on many topics in biology, but his pioneering development of the Hopfield network revolutionized our understanding of neural processing and laid the foundation for modern computational neuroscience and artificial intelligence. In the early 1980s, John sought a very hard problem to work on: how the brain stores memory. His 1982 PNAS paper on associative memory introduced the concept of computation through dynamics of a neural circuit. In that case, the problem of completing a memory given only partial information. And this idea gave route to an entire field known as computing with attractors and contributed to modern machine learning methods. In addition, his theoretical ideas on attractor networks have now been found to be instantiated in circuits in the brain to support persistent neural activity and memory, bringing his ideas full circle back to neuroscience. I'll just end by saying that through his recruitment of faculty in molecular biology in the early 2000s, John also helped lay the foundation, together with colleagues in psychology, for what would become the Princeton Neuroscience Institute. And John Hopfield has also been an extraordinary mentor and colleague. When he is in the P&I building at his emeritus faculty office, there's often a long line to visit with him. His work has touched many people at Princeton, many of you in this room, and around the world, and we are so happy to honor him today.
Thank you, Mala. And I think we're now going to turn to Professor Jim Olsen, the chair of our Department of Physics.
Thank you. I am honored and thrilled to be here and on behalf of my department to congratulate you, John, on this well-deserved and, at least in our department, long-awaited award. John was a faculty member in our department in the 1960s and 70s. He is a visionary scientist who transcends boundaries and illuminates the deep connections between theoretical physics and a wide range of phenomena across myriad fields of science. President Eisgruber mentioned a tradition at Princeton of scholarship, which includes teaching and research. And I was asked this morning for evidence that John taught undergraduates. And so in the chair's office, we have all of the course catalogs going back to the 1930s. And I was able to quickly confirm that, John, you taught Physics 103, 104 in 1967 and 68. Not only taught it, he was the director of the course, and he was doing what we would call double teaching today. So John is a scholar, and we really appreciated his impact on the department throughout the decades. John was a passionate teacher in our department and a mentor to undergraduates, generations of undergraduates and graduate students who were inspired by his brilliance and unique approach to studying nature. We are so proud of John and so excited, and because it's not my field, what John works in, I have a quote here from a colleague, Bill Bialik, who's in the physics department, but also at the Lewis Sigler Institute, who said, quote, "More than any other individual, John saw how a theoretical physicist could engage with the beautiful and sometimes mysterious phenomena of life. His work has ranged from allostery in hemoglobin to electron transfer and photosynthesis, and from kinetic proofreading to the ideas about neural network dynamics that were recognized today. He inspired and influenced many of us directly and indirectly now over many decades." Thank you, John.
Thank you, Professor Olsen. And with that, Professor Hopfield, we turn it over to you, and we'd be honored to hear directly from you.
You talk. Say something. You're on, John. Just say something. Talk about your work.
It should be
Talk about your work. You talk, yes. John,
So what do you want?
John, just talk about your work.
So should I start off with the question of biggest fears, biggest hopes?
Yeah, I think, John, it sounds like you're going to some of the questions we've had from reporters. That's fine if you would like to do that, but we would all love to just hear from you on any thoughts that you might want to offer if you would like to do that. We may be having some trouble with the technology here.
Well, of course, the thing which I know best about is trying to fit something which does not fit into a university, into a present university or teaching framework very well, and trying to work with that in such a way that it gets modified and the institution gets modified, and so that something quite different actually in the long run is developed in the institute educational program. When I first worked in the areas for which I had been given undue honor, they were disciplines, and you didn't cross discipline boundaries. A gentleman biologist does not venture an opinion about a physics theory, for example. In the long run, new fields of science grow up at the intersection of big chunks of science, which are the pieces of knowledge now. And you have to be willing to work in those interstices in order to find out what are the limitations of the knowledge that you have and what might you do to make the subjects richer, deeper, better understood. So if I turn to this immediately to the issues of neural networks, they're often said to be neither neural in the sense that they violate huge numbers of the sacred cows of biology. And they are also things which are only approximately true in the mathematics. And yet you bring these things together and you get a subject, in some sense, you build a truth out of partial truths. And you have to have a framework in which you can do this. A teaching framework is a very good one. One of the reasons I came to Princeton originally from Berkeley is that the faculty was actually interested in teaching, whereas in Berkeley had reached the gargantuan size, which made that impossible. So you can develop a course which is interdisciplinary and has this life of its own if you have students who want to take the course. And that was another thing which was a very helpful part of my life here at Princeton. It was in its way much more helpful than the support which departments tended to give, which tended to be forces which said, stay where the center of gravity is. Don't go out the fringes. That's fringe stuff. The way to build a strong physics or a strong biology department is to know where the center of your field is. That's a way to build a kind of department, but it's not the only way. And if you want something which is inventive and it may be a disaster, but maybe a triumph, you have to go out and work in the interstices some. And that's what, to me, is part of the problem of making a good curriculum, selecting a good faculty, selecting students who are interested in the kind of science which has such extensive possibilities, as well as being the possibility that you just don't find anything at all. A risk you have to take. That's all for that one at the moment. I can come back there, but I might better, from the list of questions I have in front of me, talk about the question of here's something which seems to be inordinately powerful compared to what you put it into it. How much power does it have? Does it have enough power to worry about? To worry about not just in a trivial sense, but to worry about what it does with respect to how people live, how the earth is run, because the earth is run in some sense by people. And I've watched over the course of my lifetime 2 technologies grow up, which had 2 parts of them. The molecular biology revolution, which took place in the 70s and 80s, enabled all kinds of things for making new biological products. Engineered viruses, engineered neurons, engineered cell lines. These things were useful, but they're also hazardous. You remember the 19 must have been the early 1970s. I was on a Princeton committee having to do with what should be the ground rules for doing what is now called recombinant DNA research, because it was obvious that it had both potential for great good and potential to be militarized or accidentally to do great harm. And before you turned this behemoth out to just develop at random by faculty members, by scientists biting off particular corners and working on them, you wanted to have some idea of how you could control the system and how you could prevent disasters from occurring. And that was, of course, built on top of the nuclear physics discoveries, which enabled both the building of the atomic bomb and the generation of power plants for getting electric power from fission or fusion. And so one is accustomed to having technologies which are not singularly only good or only bad, but have capabilities in both directions. And as a physicist, I'm very unnerved by something which has no control, something which I don't understand well enough so that I can understand what are the limits to which one could drive that technology. That's the question which AI is pushing, and is pushing very much because of the neural network things which have come forth from physics and computer science and now seem absolute marvels that you don't understand how it works. Very, very unnerving. And that's why I myself, and I think Jeffrey Hinton also, would strongly advocate understanding as an essential need of a field which is going to actually develop some abilities that are beyond the abilities that you can imagine at present. Okay, enough for that one at the moment.
Professor Hopfield, thank you for. Let me summarize for the audience the questions that have been submitted that you have before you. Just so we've got a question. You've answered the first question was from the Associated Press about hopes and fears for humanity as a result of some of the discoveries. This next question is from the Washington Post, and Lizette Ortega from the Washington Post asks, some people are wondering how the work awarded today, which has revolutionized computer science, fits within the field of physics. What would you say to them? How does your work fit within the field of physics?
Well, I would first ask, what defines the field of physics? If you say it's what physicists do, there's a tautology there, and you can move the whole enterprise over and still call it physics. But more fundamentally, what is physics? In my view, physics is trying to understand how systems work. The systems are made of parts. These parts interact. So when you make large systems, they get behaviors which are different from the way small systems behave, and in fact can be fundamentally new things. When you get systems which are rich enough in complexity and in size, they can have properties which you can't possibly intuit from the elementary particles you put in there. You have to say that system contains some new physics. And in trying to understand the brain, there are so many questions which you can't even make any plausible suggestion for how they work, let alone find evidence for that in biology. There's so many things of that sort that you have to say that there's going to be new physics found in understanding how the brain operates. And I think that that's true. And of course, if you look at neural nets as they are in mathematics and as they are built into computers, 99.9% of the details of biology are omitted. Everybody runs with their phone. And so it's once you get a system which is big enough and complex enough, it has properties which you, from simple arguments, explain. And at that point, a new idea comes forward. There are going to be collective properties which are not properties of the elementary units of something, but which the units produce. And condensed matter physics gives an introduction to how such things can come about. My former friend Phil Anderson, dead now, another Nobel Prize. His most famous paper was, I think, called "More is Different," trying to explain how there was new physics coming out of large, complex systems. And if you want, that paper is slightly dated, but for a paper written in 1973, I believe it was, it's still very well worth reading. But so in short, I think that in biology, and in particular in neurobiology and immunology, there's new physics yet to be understood. And the problems are such that if you don't understand, if you're not motivated by physics, you just don't tackle that class of problems.
Thank you, Professor Hopfield. We have one last question. I mean, I'm combining two questions, one from the New York Times and one from National Public Radio, who asked basically the same question. They said, Dr. Hinton, your prize co-winner today, has been quite outspoken about the dangers in the usage of unregulated artificial intelligence. The question is, do you have any perspective, opinions, sentiments about AI, where it's headed, its usage as it continues to spread? What are your views?
The worry I have is not AI quite directly, but AI combined with information flow around the globe about everything you would like to know. And so you get more and more tempted to say, I know everything there is to know, I can figure out how things work. I can predict how things go. And I think the autonomy of individual units, call them people, comes into collision with everything known by something or other, which then feed back information and change things. And so I'm worried about a world of control. The 3 decade later generalization of 1984, what 1984 was written about, was written before anybody had any ideas of what you could actually do in the way of information transmission and information in the way of controlling information interactions in such a way that you can actually control a very big system with some kind of simple algorithm, which is very successful, but you don't understand how it works. Now, at that point, if you don't understand how something works, you don't know that the collective properties you began with are actually the collective properties of the system when you all have all the interactions present, and you don't therefore know whether some spontaneous but unwanted thing is lying hidden in the works. The science fiction, what was it, Ice 9, the premise that ice had a different structure than that which is normally expected for one of the known phases of ice. And that once this was seeded, the whole crystal would spread and it would basically wipe out life as you know it by tying up water and putting it in another substance. And of course, the whole area was spurned now of polywater was actually about that many years ago. But I worry about anything which says, I'm big, I'm fast, I'm faster than you are, I'm bigger than you are, and I can also run you. Now, can you peacefully inhabit with me? I don't know. I worry.
Professor Hopfield, thank you so much for letting us spend some time with you this morning. To those of you who are listening from around the world, thank you for joining us. For those of you who are here with us today, the many of you who are here with us today, we'll have a reception upstairs following this news conference. Please join, and Professor Hopfield, we'll look forward to seeing you on your return to Princeton soon. Everyone, please join us in another welcome, a round of applause for John Hopfield today.